Welcome to the Explainer. So today we're going to completely demystify Python's abstraction models. If you've ever stared at a massive, chaotic codebase, just kind of praying for some sort of structural sanity, you've probably bumped into the concepts of abstract classes and interfaces. But look, instead of just repeating surface-level definitions, we are going to look exactly at how the core technology works under the hood. We're breaking down the mechanics, the actual code, and the crucial differences between them. All right, let's dive right in. Here's our roadmap for today. We're going to cover blueprints for Python code, abstract classes in ABC, Python interfaces with Zope, and finally, a technical showdown, abstract classes versus interfaces. Okay, section 1, blueprints for Python code. We're setting the standard for functional units. Imagine you're an architect, right? You're tasked with building a massive skyscraper. You wouldn't just start laying bricks randomly. No way. You'd create a blueprint. Well, in object-oriented programming, especially when you're building huge functional units in your codebase, an abstract class acts exactly like that blueprint. It's this foundational structure used to define a collection of methods that are absolutely required for all subclasses derived from it. It essentially forces any connected subclass to follow a very specific set of structural rules. It gives you a standard interface for all the different implementations of a component. Now, the truly fascinating defining feature here is the abstract method itself. An abstract class must include one or more of these. But what does that actually mean under the hood? Well, it means the method has a declaration, a name and expected parameters, but absolutely zero implementation. The code block is literally empty. It acts as a strict placeholder, just sitting there waiting for the subclass to step up and do the actual heavy lifting.
Moving on to section 2. Abstract classes and ABC. This is Python's built-in blueprint tool.
So here's where Python's unique approach really comes into play. Python actually doesn't have abstract classes built into the core language syntax by default. I know, a bit surprising, right? Instead, it relies on a core built-in module called ABC, which stands for Abstract Base Classes, to give us this exact functionality. And to make this work mechanically, the process is actually pretty elegant. First, you just import the ABC module and the abstract method tool. Second, you decorate your base class methods. And third, you register concrete child classes as implementations of that abstract base. Let's actually look at how this operates in the code. The crucial point here is how you construct that base class. Say you create a class, let's call it animal, and pass ABC right into it. Then, for any method you want to mandate, say a move method, you just pop the @abstract method decorator right above it. Under the hood, this decorator acts like a bouncer. It actively prevents Python from instantiating the animal class directly. Plus, it'll throw a strict error if a child class tries to run without providing its own specific code for that move method. And this brilliantly illustrates what happens when we do it right. We build our concrete driver classes, human, snake, dog, and lion, and they all inherit from that animal base class. Because they all successfully implement their own distinct version of the move method, Python registers them and allows them to execute. And the output perfectly matches their specific mechanics, right? The human walks, the snake crawls, the dog barks, and the lion roars. Boom, the blueprint is fulfilled.
So that covers Python's built-in ABC module. And hey, it's fantastic for standard inheritance. But what if your project scales up and you suddenly realize you need even stronger semantics? What if you're building a massive API where you need highly specific object interfaces, and frankly, much better error messages than what the standard library provides? That brings us to section 3, Python interfaces with Zope, stricter semantics and better error messages. To solve this need for strictness, the Python community often turns to a third-party package maintained by the Zope Toolkit project. It's called zope.interface. But first, let's actually define an interface in this context. An interface is a strict set of method signatures that an implementing class is fully expected to provide. Think of it this way. While an abstract class is all about shared foundational DNA, an interface is purely a behavioral contract. It's a tool for writing highly ordered code where an implementing class is strictly held accountable to specific signatures in order to achieve abstraction. Let's unlock how Zope actually functions under the hood, because it uses a very distinct vocabulary. First off, any interface you build must subclass interface.interface, which acts as the parent for all interfaces in the system. The package directly exports two core objects to build with, interface and attribute. And finally, the binding mechanism, like how a class actually adopts this contract, is handled by the @zope.interface.implementer decorator. Let's see this in a practical code snippet to make it concrete. Here we're declaring our interface, called myInterface. Now notice that we aren't writing traditional functions here. We are simply defining rules.
We declare that any compliant class must have an attribute named X, which we describe as foo. We also dictate that it absolutely must have a method 1 that takes an argument and a method 2. All of these just use the pass keyword. They are purely structural rules, entirely devoid of any actual logic. So now for the implementation mechanics. How do we actually make a class follow these strict rules? Step 1. We place that implementer decorator right on top of our new class, passing in my interface. Step 2. We define my class. And step 3, we provide the actual executable code. So for method 1, we might write a logic block that returns the square of the input, and for method 2, we might just return the string foo. The interface acted as the blueprint, but my class actually built the house. And the final result proves the mechanics are working perfectly. We create an instance called obj1 from my class. Because my class strictly implemented my interface, the instance provides the exact behavior we promised. We feed the number 5 into method 1 and get 25. We call method 2 and get foo. Under the hood, we've achieved a highly structured abstraction where instances can confidently interact based on known, strictly enforced interfaces. All right, section 4, abstract classes versus interfaces. It is time for the technical showdown. So we've seen exactly how both of these core technologies work. But the golden question is, when should you use which? Let's put them head to head. First up, method composition. An abstract class is pretty flexible. It can contain abstract methods that force child classes to do work, sure, but it can also contain regular, concrete methods with fully functioning code that child classes simply inherit. An interface, on the other hand, is uncompromising. Every single method in an interface is strictly abstract. There is zero inherited behavior here, only inherited rules. Next up, let's look at their primary use cases. Basically, you want to reach for an abstract class when there are common, foundational features shared by all your objects. If all animals breathe exactly the same way, you put the breathe code right in the abstract class. But if you're building a system where features must be implemented completely differently for different objects, you use an interface. The interface just guarantees that the objects can do something, while leaving the how entirely up to the uniquely tailored implementation. Another absolutely crucial difference comes down to responsibility. With an abstract class, it's typically the original developer's responsibility to create the child classes within their own internal structural hierarchy. Interfaces, however, act a lot more like public contracts. Very often, a third party, like another developer using your library or your API, is the one responsible for creating the child class that fulfills those strict interface requirements. And of course, we cannot ignore performance under the hood. The built-in abstract classes using the ABC module are natively integrated and comparatively fast. Zope interfaces, well, they provide incredible semantic power and strict error checking, but because they run via a third-party framework layered over Python's object model, they do introduce a bit of overhead, so they are comparatively slow. To summarize this whole technical showdown, here is your definitive cheat sheet. If you need a mix of concrete and abstract methods for shared features built internally with high speed, use the ABC module. But if you demand that all methods are strictly abstract, requiring unique implementations by third-party developers, and you don't mind a slight speed trade-off for stronger semantics, well, Zope interfaces are definitely your tool of choice. And that brings us to the end of our explainer. We've gone under the hood to see exactly how Python manages abstraction, both through the built-in ABC module and the strict semantics of Zope interfaces. Both are incredibly powerful ways to bring order to chaotic codebases. So the crucial question I want to leave you with today is this. Take a hard look at the architecture of your current codebase. Are you building a family of related objects, or are you enforcing strict public contracts? Choose your blueprint wisely. Thanks so much for joining me on this deep dive, and keep building great things.